Welcome everyone to the second session of this morning and the last session for today. And our first speaker is Amal Ahmed. She's going to talk about formally specifying ABIs using realistic realizability.
That realistic realizability is a bit of a mouthful, right?
Yeah,
I'll tell you who to blame for that in a few slides. All right. Okay, so I'm going to talk about ABIs. So let's just start a bit broadly by talking about what is an ABI. ABIs specify things like data layouts, calling conventions, name mangling in safety invariance, perhaps, ownership invariance. ABIs are also one of those mysterious kinds of things. You know, developers for years talk about ABIs, and I always kind of tried not to look. You know, they're messy, they're complicated, they're too low level. And I was like, yeah, okay, that's a thing, and I don't care. But apparently I should care, and I'll explain why. We all should care. So basically, what ABIs are really useful for is, you know, they allow you to think about linking about how you're going to link output of different compilers. It might be two different compilers for the same language, or you know, it could be language interoperability and FFIs. And also to think about libraries that you might develop in your language, and as developers evolve these libraries over time, are they still usable by the old clients of the library, and so on. So let me get into a little bit more detail about those kinds of applications. So first, let's talk about compilers. So let's say I have a language. This is a blue language, so it's one language, but I'm thinking about two different modules in the same source language. And I want to compile them using different compilers and produce some target code. But if those two compilers are doing something slightly differently in terms of layout or calling conventions, et cetera, low-level details, then we might not be able to link them together, right? So there's a question of whether or not we can. If the two compilers are ABI compliant, then we can, because they've promised to kind of stick to the agreed upon data layout calling conventions and all the other details. Next example, libraries. So let's say I am a client, and I'm using some library written in the source language, and I'm labeling it slib1 because that's my version 1. And these are compiled down to the target code, and right now we know that they link together perfectly. They interoperate. You know, I as a client can use this library. Everything is good. But sometime in the future, suppose that the library developers decide to publish an update on this library, producing this version 2. So how do I know that this is still okay? And this is also something that we can use ABIs for in order to answer that question, because I really need to know, like, is the library doing basically the same thing? Like, let's say the library added some fields to a struct. They weren't in the original struct or something like that, or added some certain functionality that wasn't there in the original library. Has it changed the layout that I was relying on, the subsets that were there in the previous version? Okay. Finally, an application that is very, very close to my heart, and those of you who know me know that I always talk about language interoperability. So let's say I have a language, a blue language and a green language. All right, so I have two different modules written in two different languages. And what I'd like to do is be able to mix code from these two languages. So how do we mix code is a whole long story as well. And I have a few slides on this after this. But roughly speaking, you know, you might have two languages talking to each other through the common denominator CFFI, or you might design something more sophisticated. We've done all sorts of work on defining multi-language semantics. How do you define the boundaries between languages? What conversions do you do? How do you make this interop more secure using something called linking types? I won't go into all of those. But essentially, what you want to do then is you want to show that whatever kind of glue code that you're using as part of that you're generating to implement your FFI. FFI are those shaded little pieces over there, if you will. That after you put everything together, that you actually are going to have adherence to some common thing. So let's just dive into this picture a little bit further, right? So you might have Rust interoperating with C, right? Rust's extern unsafe, for example, right? You just use the REST FFI to do this. And this is fine. But what I want to talk about is situations like where you have a nice language like Rust interoperating with a nice language like Haskell. Both of them are type-safe languages. What happens in the previous picture, the slide that I was on here, is that C is incredibly unsafe, and so when you use an FFI with C, you don't really know that C isn't kind of, damaging all the nice Rust invariants that you have in your Rust module. So it kind of leaks into your language, let's say. And, whole separate issue, we would like guarantees that that does not cause unsafe interrupt. But here, I have two safe languages. It would be nice if I could design an FFI directly between them, between Rust and Haskell, but that doesn't really exist in practice for the most part. Most languages end up, even safe languages, end up interoperating by dropping down to the lowest common denominator, C. So I want to use this observation as a kind of step into why do most languages, even really good type-safe languages, end up interoperating through this by using the CFFI, by dropping down to this kind of lowest common denominator. C doesn't give us very many guarantees. These languages do. They kind of forget about their guarantees and then start interoperating through this unsafe C. So why C? The shallow answer, we'll all say, you're probably thinking this already, is that every language speaks C. Every language has a CFFI because we need to link to standard library stuff, etc. But why does every language speak C? And perhaps the deeper answer here is that C is one of the few languages that is committed to what we call ABI stability. And they say that this is our ABI, and we promise everyone in the world that it will not change over time. So ABI stability basically says, yes, C has it for any given platform, and an ABI is basically specified for, we normally have a family of ABIs for every source language, right? One for every single platform. So for C, we basically have this promise of that C will have this ABI today, tomorrow, forever. Why do other languages not want to commit to such to a stable ABI? So Rust, for example, there's been a lot of conversation in the Rust community. Do we want to commit to a stable ABI? Sort of, there's resistance to this. And why is that? Because why do we want to perhaps allow changes over time? Because basically, it's the cons of a stable ABI. It limits your choices in terms of what your compiler can do. If in the future you want to add a certain feature to your language, and that mandates that you can do certain things better or change layouts in order to handle things in a more, in order to do optimizations, for example, et cetera, you may not have the freedom to do that in future versions of your compiler once you've committed to a stable ABI. So the cons are, can stunt language growth. Maybe you can't add a certain feature because it messes up certain guarantees that you promised the world. Limits compiler optimizations. There's also this tension between flexibility and performance, which is, I'll talk about this later in the context of Swift. But basically, it's this issue of, let's say I want to extend a library. I've talked about this before, like I want to add some fields to a struct or some functionality to my library. How do I, or perhaps I want to reorder the fields of a struct. How do I deal with situations like that? In order to get flexibility, you sometimes have to give up on performance because you might ask the clients of the library do one extra level of indirection to figure out what the actual layout is. So it limits flexibility. So C goes for performance, not flexibility. Swift is trying to go for flexibility without sacrificing too much performance. I'll talk about this a little bit later. And then there's pressure on library developers as well. And I sort of skipped the pros and just jumped to the cons. But what are the pros? If my language has a stable ABI, I have sort of this precise control over my interface to the other languages. And anyone who writes libraries in my language, they can promise a certain interface to clients. So proper support for shared libraries. So I'm very much in favor of stable ABIs, but I do think we want flexible ABIs. So I think there's a lot of work and research to be done in this field. And again, Swift is a really good example. They've been pushing how far we can go in terms of not sacrificing too much performance, but gaining more and more flexibility. And there's something called the Swift ABI Stability Manifesto that I highly recommend people take a look at if they're interested in this. Yes, Mike?
May I ask, I realize a slightly stupid question, which is, so you said that Rust doesn't want to commit to a stable ABI, but it also supports the C ABI, which is stable.
Yes.
So why does that not constrain their freedom of movement?
Right. Okay, so that's a very good point, and I should have clarified. So perhaps a question, stepping back, that we should ask is, what should an ABI specify? When Rust is completely committed to the C ABI, but the C ABI is very poor in terms of what it promises you. I think that what a language's ABI should include is all of the type level guarantees that the language provides. Wouldn't that be nice, right? In Rust's case, I would say that an ABI should also specify its ownership and borrowing invariance. That would be lovely. Then we would know that this is the Rust ABI. If I want to link with Rust, I need to make sure I don't go disturb those ownership invariants. That's a much richer ABI. But moving to a world with those richer ABIs requires, saying, okay, we're fixing things. And there's a resistance to that. So Rust, in terms of adoption and so on, right? The call that they've been making is that we will stick to the C ABI. That's what we promise, but they're not promising what their language actually gives you. They're not putting that into the ABI. Even the Krabby effort is staying away from that. Okay, that's why I have safety invariance and ownership in italics and the others not, because the others we all kind of agree on and they've become standards. But should an ABI include ownership and safety invariance is a question that we very much still need to push the envelope on. Okay, yeah. So who cares? A lot of different languages do care. This I just talked about the ABI Stability Manifesto from Swift. Rust, there's an effort called Krabby going on, and then C++, the WASM component model is in some sense an ABI. So what I'd like to talk about in the rest of the talk is how do we go from the current world where ABIs are specified in prose to a world where we could actually write down formal specifications of ABIs, and then do some of the things, the three things that I showed you at the beginning of the talk. Show that my compiler is ABI compliant, show that my libraries are ABI compliant, show that FFIs that I design and implement are also, ABI compliant in the sense that they're actually properly allowing interrupt with the other language. Let's talk about how we might provide a formal foundation. So now we're getting into the details of what this technique is that I'm proposing. So what is an ABI formally? Basically, for a given source language, you're trying to say this source interface, or perhaps the types of the source language, mean a certain thing or guarantee a certain thing after the code from that source language has been compiled to a target. So this source interface describes target programs that, like this. That the shape that they should have. What I'm going to do is use an approach where basically types, blue types for the blue source language, types in the source language are going to be given a model as sets of terms from the target language. And these are only, so a type tau is going to be, I want you to think of it as sets of target terms that adhere to whatever that type says. So if it's a struct, and the type needs to be laid out in a certain way, then this code needs to be laid out in that way, right? Or calling conventions, or other things like ownership invariance, etc. The term realistic realizability comes from Nick Benton, so he's the one you should blame if it's a mouthful. But basically, this is because what we're doing is we're talking about what are the real target terms, or what is the real code that realizes the behavior of this particular source type. At the bottom, at the target level. Okay, so this is an approach to building semantic models where the source types are inhabited by target terms. And that way we can describe low-level layout and calling conventions. And then we say that a target, that's the code that we've produced, T, is ABI compliant with the source type tau if it belongs to that set tau, so to speak. That's the high-level view. Okay, Now, the question we should ask as we build such models is, have we actually provided that model then serves as an ABI spec? Is it a good spec? And once you have a spec, what you should do is, ask the question, does it capture all the pertinent details that the language is promising you? Can it be used to, in all of the relevant scenarios, such as, is my compiler compliant, etc. So I want to dive into the details with a case study to show you what these look like. This is something, we did this as a case study where we took a simple functional source language. It has recursive records and variants, higher order recursive functions, and we compiled it to a C-ish target. And basically, we are giving ABI for the functional language for the C platform. Now, this is actually something that the Krabby effort is doing as well. They're really giving Rust, they're trying to specify Rust ABI at the C level. So, normally we think of ABIs as, x86, right? But it doesn't have to be. You can do it down to a higher platform than that and then go from there. Okay, so our C-ish target has block-based memory, pointer arithmetic, kind of close to ComSort model, not exactly. But what I'm going to do is this functional language is going to be have a reference counting implementation. So at the target level, we want a sort of reference counting ABI. All my values are going to be boxed, and they're going to be reference counted. And I'm going to show you a separation logic spec for reasoning about proper accounting of shares, of reference counts. Okay. Okay, and yeah, we did this as a case study, like a first thing. It slightly, Swift is, for instance, reference counted, so we were inspired by that. We called our language Quick. It's an OOPSLA 24 coming up next month. Okay, so let me just talk about the approach. So normally when we have syntactic typing at the source level, we say that some term E in an environment gamma has type T. I want to now talk about target terms, the red E or orange E. What does it look like, red or orange?
Black.
What?
Black.
No, the middle one.
Red.
Red.
Thank you.
Red.
I'll say red. Okay, so the blue is source code, red is target code. What I want to talk about is, does the target code red E in, sort of the equivalent of the source environment gamma, have what the source type T dictates, behave the way source type T dictates. So in a pre-state like gamma, if I run E, I would like to get a value V that behaves like T. Yes?
How many colors am I supposed to see on that slide?
Projectors mess everything up. Okay, there's a blue source language, there's a red target language, and the black is meta.
But you can see boldface.
I'm colorblind.
The bold stuff is
Blue and red is getting mixed up?
yes.
I just want to know how many
Red and black. Two.
There are blue, red, and black.
Three.
Yeah, there's black as well. Oh, okay, we need to change these slides. On my screen, it's very orange, but maybe the blue's too dark.
Two lower user red and top ones.
But the bold is target. The bold E is target, and the not bold E in the very first line is source. So maybe that helps at least a little.
Let me just get my ruler.
And I should use my pointer. Source, target. This is red as well. This is target. Sorry. I like using colors, but for papers we use those filters to check for color blindness. Okay, so what we actually want is to build a semantic model or a logical relation, except that it's indexed by source types and inhabited by target terms. And the way I want you to think about this here is that given some set of inputs, so if gamma specifies a bunch of x's that have a bunch of types tx, then given a whole bunch of inputs that satisfy gamma, if I run this target code E, then I will get back some value that behaves like a value of type T. Okay, so the source language says what behavior we want, but the target terms are the things that need to behave that way. Okay, now I'm going to talk about a reference counting implementation. So I need to talk about reference layouts before I can sort of move further. Okay, and this is more scary than it looks more scary than it is. So I'm going to use this RT kind of predicate to say This basically says that the location L is a reference to something of type T. Okay? And what is a reference? Well, it's a layout question. The way that we're going to represent references is we're going to have right here in location L a reference count. So physically in memory, for every object, we're going to have the reference count stored right here. And at the next location, L+1, we're going to have the actual object payload for that reference, okay? And so I want you to think of that as at L+1, there's an object of type T, okay? Which might be another reference if that's what the layout demands. But I'll show you examples in a second. Okay, so if I make that T an actual int, then we can sort of dive further and say, okay, so now I have a reference to an integer. And right here, I have the reference count for that object, and here I just have the actual object, which will be nothing more than a number. So this basically says at location L+1, I have an integer, which means that at L+1 points to separation logic. There's a number n. Okay, so just references are reference counts and object payload. Yeah, later I can talk about unboxed data, but through most of the talk I'm going to talk about boxed values. Okay, so now the next thing that I need to talk about when it comes to reference counts is if L is a reference, well, what does that mean in terms of ownership and sharing? So a single reference like this represents one share of an underlying object. So all that RTL tells me, that L is an RT tells me, is that if I physically go and look in memory, there's at least a number that's 1 or greater sitting over there. So I have a reference count of 1. Now, if I have more references to it, then I know more. So if 1, 2, 3 references, that means the number over there is 3 or more. There might be other references, so it might actually be 5. There might be a couple of other references out there. Okay, so I'm basically trying to show you that this RTL is our semantic way of defining a single share to a single reference, a single share of the object. Okay, having a share confers permission to increment the count. So if I decide to increment the reference count, I already have a reference, and I decide to increment the reference count. What does that mean? That means that afterwards, I know that the reference count will be greater than 1, and I know that I'll have 2 references. Okay, so I have 2 shares because I incremented. I can also decrement if I have a reference. So as these references go away, we will reduce the count. And we have a rule, separation logic rule again. If I decrement the count, I had a reference, I decrement the count, then either there might still be other references out there. Either n is greater than 0, the number of references to this object is still greater than 0. Or it might be the case that n has become 0, that my decrement just went from 1 to 0 in physical memory. In that case, n is now 0, and I get back ownership of both the location that is storing the reference count and the actual object payload. Right? So these are very simple, this is separation logic stuff, but like how we get into the details of specifying an ABI is the critical bit here. Okay, let's see. So I want to talk about initialization. When we go from actually creating the object at the beginning. So sorry, my animation here, this was, I'm trying to create a reference to something. I have an object payload at location L+1, and I have a reference count of 0, and I want to create my first reference to it. Well, we have a rule for initialization, which basically lets me take, once I've incremented the reference count to 1, and I have my object payload, I can view that as a reference and continue. Right? So it's a logic for reasoning about programs that are doing all this work. The next thing I want to talk about is like, how do we validate these rules with the semantic model, right? So far I just showed you a bunch of separation logic rules for reasoning about the code and its behavior. So now I'm going to show you the actual realizability model part. So we'll have a semantic model that captures invariance on resources. I'm using that word generally for just a moment. Now, normally, when we think about separation logic propositions are predicates over heap fragments, right? Locations point to things stored at those locations. But what we're going to do is we're going to sort of have richer resource, logical heaps. The logical heaps are going to keep track of, we need these logical heaps in order to keep track of reference counts. So logical heaps will map locations not just to values, but to whether the value is owned or shared. So owned or shared, so an owned value or a shared reference counted object. Okay, and what do I mean by that? It looks like this. A resource is a mapping from locations to either owned vals or shared things with two pieces of information in them. My share count, the n, and the actual resource, which is the object payload. Okay? And then you have to think about how do I put resources together. And you know, the critical thing here is that at any point in time, if I'm this part of the program, I don't know what other references are out there to the object that I'm pointing to from other parts of the program. So I can only talk about my view. So that's why we have to use this very like compositional sort of separation logic view of things and be able to put together shares of resources. Okay, so we can put together resources if you know, they don't talk about the same locations at all. That's just do a disjoint union. But what's interesting is if I have a location that I have shares in one part of the program that have perhaps n1 references to this resource or object row, and I have another part of the program where I have these another n2 shares, then I can put them together. I can add them up. Right? So that's the rule for composition there. So again, separation logic, just different ways of combining given what our resource model is. Okay, so let's just talk about some, oh, actually I have to just want to define this. So then in the end, what a reference is we use this thing, we've defined this thing called a jump modality, which basically says you should think of a resource as a tree of objects. And when I say at LP, that means that you can jump across location L to reach some object that satisfies a predicate P. Okay? And the interesting bit here is that any particular at P will only give you one share to that object. Perhaps this is getting a little bit in the weeds. Let's just talk about how we lift this up to object layout. It all just follows pretty naturally. When you have pairs, now this is an object, not a reference, right? When you have pairs, that means there's an L1 that points to there's an L1 that points to a reference to a T1. There's an L2 that has a reference to a T2, right? So that's how we represent pairs. Now let's get into slightly interesting things. So here's a struct. It's a point. It has two fields, X and Y. Yeah.
Sorry, so your pair itself is not referenced.
What happened is that I was showing you only the object payload.
Oh, okay.
Yes.
That's
So this is the thing on the inside, and
reference.
if yes, L-1 is the place where the references start. Yep, it's ref-handed. Okay, but thank you. Important clarification. Okay, so for this struct, we're just going to say that at L we have Lx, which is the pointer to the first field, the integer. At L plus 1, we have Ly, which also contains an integer. And this is basically what the CABI would do. Okay? But what the CABI is sort of ends up meaning is that you don't have reordering of the fields. This has a fixed order in which the fields are laid out, right? And the ABI is specifying that. And you also don't have extensibility. So if I later wanted to come in and add in a field Z, I can't do that. This is it. So how do people deal with things like, being able to develop extensible libraries? Like, let's say I have a struct, and I want to be able to extend it in the future. So maybe I do want to add that Z field to my point struct later. The way that people end up doing this, developers end up doing this, is that they give themselves the option for more in the future. And that means that in the future they might update the library and encode things this way, right? You have X and Y like you did before, and now you use that option to actually store a point Z, where you give yourself more option to like chain through and put more things there. It's a mess. I'm trying to say that the CABI's decision to be rigid has consequences like this. Okay. All right. And I guess the other thing I'm trying to show you is that by writing down these specifications, we kind of start to see those consequences really clearly as well. Okay, so Swift, I want to talk about that for a minute. It takes a very different approach. It does support reordering and extensibility for structs. What they do is, rather than fixing the offsets, they ask that clients dynamically query them. Okay, now that's an extra, that's a level of indirection, right? But basically, how they support this is that along with every struct definition, their library will include top-level definitions, which give you the offsets of all the fields in the structs for that library. The client only learns what the offsets are when loading the library, but the library, internally, the library doesn't need to go look up the offsets because it knows what they are. It knows them statically. Yeah, but the clients use this indirection reading through the table, which gives them flexibility across releases of the library. So just to show you again what this looks like, a client has to go look things up in the offset table, and once they look up OX and OY, they know where the offset is and they know where to find the references to those fields. From the library's point of view, they actually know exactly statically what the offsets are, so they know where to find them. Yes?
So I know nothing about Swift. It seems that this would be an easy use of load time specialization, just applying to locations across the compiled object file. Do they really indirect?
No, they actually have other little tricks as well that I can get to later. Yes. Okay. And just to semantically show you what that might look like, it might look like, it ends up looking like a definition like this. Again, looks hairy, but it's very easy. For struct point, there is this top-level definitions table. That's where I said they store the offsets for all the resilient structs that they have. They might have non-resilient structs as well. You totally have the option to define, to go with a rigid layout for structs. And this basically says that, you know, there's an L, and at offset X, I will find LX. At offset Y, I'll find LY, and I need to look up the offsets from my table D, and that's just what I find at LX and LY. And then there's this top thing, which allows for extensions. You can add things to the struct later on. From the client's perspective, that top means that, you know, anything else in the struct is completely opaque. Okay, so this is the definition that the client would see, and the library's semantic view of it would not have a top there, it would have the actual details. Okay, calling conventions, the other thing that, important thing that ABIs specify. So first, let me show you a very simple kind of version of this. So for a function, T1 or T2, if I want to say that L behaves like an object of that function, so I'm just saying that L points to a function, oops, I was trying to use the laser pointer. Okay, so L points to a function f, and what do I need to say in terms of behavior for that? I need to say that if I apply f to some input L1 that is a reference to a T1, the argument type, then afterwards I will get back an L2, which is a reference to T2, which is the result type. So, and I can also point out that you can think of this little calling convention and compare it to this alternative. The top one you can think of as caller retains the access to the L1, and the bottom one is callee retains. So here, the function after calling L1 and after it's done running, it also gives back a reference to that L1. But you know, you can encode these different calling conventions at this level, the details of that. I won't go into closures, but closures have more complexity. There's self-reference that needs to be passed. Call is the function that needs to be called, but there also has to be a destroy function that cleans up the environment afterwards when you're done with, when you have 0 references left to that object, to that closure. I'll just skip over that though. Okay. And then there's unboxed data. You can set up a model where so far I've said that all my values had were boxed, but suppose that you use tagging to say which values are going to be boxed and which are not. Okay, so here just to sort of start off and point out, my location is actually a block and it's offset, concert-like model. And let's say I want to talk about, let's say this T is a struct type and structs are always going to be boxed. Then my definition of this will look something like this. You know, 1 is the tag that says this is a boxed type. And at L minus 1, so L is the actual object, but at L minus 1 I have a reference count for that object. Or we could have the unboxed scenario. So here's a tag which says this is unboxed data. And for that, we'll just say that at B, I have something unboxed of type T. And then perhaps we could have some types which are sometimes boxed and sometimes not boxed. You can handle that this way. This says that it is unboxed, so B is a reference to T. This could be, again, this would be where T is a function type. This says that it is actually boxed, and in this case, we need to talk about the actual reference at L minus 1. Okay, so just options for specifying all of these things.
Question.
Yes.
What's L minus 1 here?
Remember I've been talking about how whenever you have a reference, at location L, you have the reference count stored, and at location L plus 1, you have the object stored.
L is a pair.
If L is a pair, then...
it's just the offset that's moving? You say L minus 1, but L is also a pair BI.
No. So if this is, let's say that instead of BT, I had over there O of T1 paired with T2. L, right? So I'm asking, is L an object of a pair type, the object payload? That means that at L minus 1, you have this reference to the pair, the reference count for the pair.
Okay.
Does that make sense?
So that equal, is that really a points to? When you say BI equals L, is it more?
Oh yes, that's just like my location representation is actually pairs of block numbers and the offsets.
So when you do minus 1,
I do a minus 1 to basically go back.
is it like BI minus 1, or is it?
Okay, think of that as there's an underlying arithmetic for doing the minus 1. Yes. What will happen is that you actually have the pair is going to be stored at an offset inside. I was just trying to abstract away from the details and not show real types, but your pair will actually be stored at an offset inside the block, and it will be perfectly legitimate to do an L minus 1 at that point within the block.
Right.
Otherwise, it wouldn't. Okay. So coming back to the applications, once you have ABIs specified, you can use them to do the things that I was talking about at the beginning. You can actually, take two different compilers, the solid one and the dotted one, and show that they are compliant. And what does that mean? A compiler is, ABI compliant if given any source code of type T, when you compile of type tau, when you compile S to target code T, that implies that the target code that you've produced belongs to this model of source type tau, right? Belongs to the set of behaviors that tau allows. You can do library compatibility. Here, if I update my slib1 to my slib2, then I want to say if I'm moving from an interface where I supported a tau1 interface to a new one where I'm supporting something tau2, then tau2 is a compatible update from tau1 if any target code that satisfies tau2 also satisfies tau1.
Could you give an example? Like I have a hard time imagining what would be tau1 or tau2 that would be?
So basically I'm thinking interfaces, right? So I'll take a very simple example. Suppose that I had a library in which I had that struct point with x and y, but in the future I've updated my library and has an x, y, and z. You're the old client of the library, you only care about the x and y. So I need to show you that even after my update, now that I have x, y, and z, I am still compatible with the old version and you can still use my new library version. So how do I do that? Or how do I get that guarantee? Basically, I want to show you that struct point with xyz is a compatible update from struct point with only xy, and that is true if the target code that I'm producing now that inhabits struct xyz also satisfies the behavioral requirements of my old type, where I only had xy. Yeah. Things like that. Okay. And here, of course, you have to think about decisions, how do you allow this sort of library evolution over time? And it really depends on whether you've gone with a flexible ABI or a rigid one. Sometimes this just might not be, certain changes might not be possible. And then FFI safety, right? So the way we want to think about this is if we want an FFI between the blue language and the green language, let's say the green language is exporting, has this FFI to the blue language, then what we want to show is that that FFI that we designed, the blue-green little puzzle piece, is implemented at the target level with certain wrappers that will do the conversions properly so that when you take code from this language and ask it to interoperate with code from this language, that you're really, your wrappers or glue code are doing the right work to change from data layouts of that language to data layouts of this language. Okay. So I just want to sort of wrap up with a couple of things. First, I want to tell you what we're doing now. So the stuff that I was talking about so far is, if you want to look at more details, it's in the UPSLA paper that's coming up. But what we've been working on recently is we've taken a baby Rust, and we're trying to do an ABI for that. But very quickly, we sort of ran into, oh, actually, I'll talk about that in a minute. Okay, so basically what we're doing there is a model of these Rust types in terms of WebAssembly code. So we're doing an ABI for the WebAssembly platform. So you give a semantic model of Rust types in terms of WebAssembly code and state. Now, when you're trying to construct a semantic model of Rust representing owned references in the semantic modeling world is very well understood. How to have a semantic model capture ownership, capture borrowing, and lifetimes, so mutable borrows, immutable borrows, and how lifetimes govern use of those. That's more involved, but again, we do have instances of such models. The sort of other really novel question that we ran into has to do with how do we modularly specify ABIs, and let me explain what I mean. The Rust compiler to WebAssembly, there is no direct Rust compiler to WebAssembly. The Rust compiler to WebAssembly compiles to LLVM, and then you compile from LLVM to WebAssembly. So in a world that looks like this, right, how do we go about modularly specifying ABIs? Like I'm saying, oh, here's a technique. How is the technique going to scale? How are we going to do these multi-pass kind of compilers, which often just get cobbled together, right? I've always thought it's really weird that Rust goes through LLVM to WebAssembly. Like you lose structure and then you try to regain it. It's odd. But that is the real state of the world, right? So if the world looks like that, the compiler goes from Rust to LLVM and LLVM to WASM. How do I construct an ABI for Rust for the WASM platform? I could take the direct approach and say, okay, I don't care about what's in the middle. I'm just going to construct a model that tells you what the WASM layout is going to be, right? But that wouldn't be very modular. And this already has real world, this is a problem in the real world because the Rust compiler developer who's writing down the ABI for WASM needs to know not just what the Rust to LLVM compiler is doing, they also need to really intimately understand everything that the LLVM to WASM compiler is doing, right? To get this right, to get the direct approach from Rust to WASM properly specified. And then what if, in a month, the LLVM to WASM compiler changes certain things? And this happens all the time. In that case, your ABI needs to change, but it's not changing very modularly. It's like a very weird, finicky kind of process. Yeah, both of these compilers might change independently over time. So this is a problem. How do we do this? In a nutshell, what we're doing is we are showing that the Rust to LLVM ABI, we're specifying a Rust to LLVM ABI. We're showing that that compiler is ABI compliant. And then we are developing a model from LLVM to WASM that is indexed by Rust types, and we're showing that that model is ABI preserving. Put together, those two things give you that your compiler will be ABI compliant, if that makes sense. But anyway, this is the usual, how do I compose multiple passes of a compiler kind of issue that comes back to bite you. Yeah?
Would you be able to reuse this to have like LLVM to normal assembly?
Yeah, so the Rust to LLVM part will stay exactly as it is, right? That ABI is specified. And then if you want to do another branch here, LLVM to assembly, you use the same approach, build that, and then they can compose. So it's much more modular in terms of effort, yeah, and specification. Okay, so just to sort of conclude, I've given you an approach that's quite hairy. It involves separation logics and fancy things, and this was really for a pretty simple language, functional language, the reference counting implementation. When you start to do this for languages like Rust or more complicated languages or garbage collected languages, ABIs are going to get pretty complicated. So the question is, how do we get to a world with ABI specifications for all our major industrial languages? If we could do that, all of our language interoperability issues might be on much better footing, and so on. But doing this work requires expertise in logics and semantic models. So if you're a compiler writer, you might understand exactly how your Rust compiler is working, and you know what the ABI is in terms of what your data layout and calling conventions should be. So maybe you could patiently sit down and start to write this out, but semantic models are complicated, and you're probably, if you're the compiler developer, you probably don't have enough expertise in doing that kind of intricate semantic modeling or in informal logics. So that's a problem. Because you really need the compiler developer's knowledge of the compiler and knowledge in how to build the formal models. So a question perhaps, or a thought I had was, can we develop libraries or DSLs for low-level target languages that capture a lot of the important concepts so that it becomes easier for someone developing an ABI for a source language to kind of plug them together and get what they want? That might be something to sort of try to build towards. And then there's this question of value propositions for companies for doing this kind of work, or value proposition for governments. Governments I can actually imagine. The US government right now would be totally on board with, like, let's do a full-on Rust ABI with ownership and borrowing, I think, because it would give them safety, right, for all sorts of code. And that's a major push right now. So I don't know if people have thoughts on that. And then, overall, I just wanted to say that, yes, it is, even after you have an ABI specified, it's a significant effort to show that an industrial compiler is ABI compliant or that your FFIs are. So it's a lot of work. All right, stop there. Thanks. That's all I have.
Well, speaker set up.
Very nice, Amal. I have a question. I mean, on your previous slide, it seems like it would be extremely difficult, that second to last bullet. I mean, proving anything about a compiler is very difficult. Proving anything about, say, the Rust, would be really, really hard.
Yeah.
Have you thought about, is there a kind of translation, validation-y, where for a specific compilation run, can you say, somehow you have enough breadcrumbs emitted by the compiler that you can, I don't know, I'm waving my hands here, that you can somehow show it's ABI compliant. So it's just, you see what I'm saying? So
yeah.
what's the if I did all this work, I wrote a very complicated API spec, I wouldn't be able to check it against the actual Rust compiler in some way, right? That's your second one.
Okay, that's actually interesting. So Benjamin was talking about dynamically checking CN specs.
Right.
I've been showing you a separation logic used to specify ABIs.
Right.
So now, if we could take my target level specification logic, which will be richer than CN, so there's a research challenge there already, and we could turn it into dynamic checks.
Right.
Perhaps that's the way.
Right.
That would be really neat, right? Because then you can just sort of check at least is this particular? Yeah, exactly what you were saying. Yeah, thank you. That's a cool thing.
Okay, sorry, Nick, no more time for questions. Thanks, Amal.